Radiologic technologists control an invisible energy force that can penetrate the human body. Now it's time to take what we can't even see and understand it. My name is Lazar Lazarovsky. I've been a radiologic technologist since 2005. I'm the host of the Rad Tech Life podcast and the creator of the 21-day Registry Review Challenge, a focused and highly structured course that follows the ARRT specifications outline, is taught by over 40 instructors, and helps students reduce overwhelm, erase anxiety, and pass with confidence. Today, we're going to cover the X-ray beam, that invisible force we create with our X-ray tube using certain technical factors that are strong enough to penetrate the human body and give us an awesome X-ray image. As always, all of the concepts you need to know are below this video, along with a free registry-style exam based on the content we'll be covering in this lesson. Now, in order to understand something we can't even see, like the X-ray beam, we need to define what it is and what it's composed of, understand the significance of its frequency and wavelength, take a look at its inherent characteristics, know how it behaves using the inverse square law, and master its basic fundamental properties. If we can grasp those 5 things, we'll understand the X-ray beam, which is a key step to knowing how it affects your patient, your X-ray image, and even you, which is something we'll cover when we get to radiobiology. Okay, we begin by defining what the X-ray beam is and what it's composed of. It's essentially a collection of electromagnetic photons generated when high-speed electrons interact with the anode target inside the X-ray tube. This is something we learned in the previous 2 lessons on X-ray production. If you need a refresher, I've included the link below this video. Now, these photons, this quanta or bundle of electromagnetic energy, exit the tube through the beryllium window and travel in a direct path toward our patient. Pretty simple. Now that we can define what it is, let's move on to the second thing we need to understand about the X-ray beam, and that's the significance of its frequency and wavelength. This is basically the way in which X-rays travel. They travel in waves that are generated at a certain frequency, which impacts the number of wavelengths it has. So the higher the frequency, the shorter the wavelength. This waveform that we're talking about here is called a sine wave, and it looks like this. As you can see here, it has 3 distinct parts. This is the crest or peak. This is the trough or valley, and this is the amplitude, which is the distance from the center or resting line to the crest or trough, depending on which direction you're measuring. So if we look at these 3 sine waves here, what would be the only difference between them? Their amplitude, right? What if we were looking at this one? What is the only difference here? Its frequency, which affects the wavelength. Remember what we said earlier, the higher the frequency, the shorter the wavelength. The distance here between one crest to another is a wavelength. It's represented by the Greek letter lambda, and it's measured in angstroms or nanometers. This here would be considered 1 wavelength. From here to here would be 2 wavelengths, and so on and so forth. We can also measure it from trough to trough. Why don't you give it a try? Look at this sine wave here. How many wavelengths does it have? Well, let's count them. 1, 2, 3, 4, 5, 6, 7. 7 wavelengths. All right, from there, let's look at frequency. This is the number of complete wavelengths or cycles that pass a point each second. If you remember, 1 complete wavelength or cycle goes from one crest to the next crest, or one trough to the next trough. Frequency is always measured in hertz, where 1 hertz equals 1 cycle per second, which again would amount to 1 complete wavelength. It's represented by the lowercase f, or the Greek letter nu. The 3 sine wave parameters then are frequency, wavelength, and there's one more we haven't touched on yet, and it's velocity. It's represented by the lowercase letter c. Velocity is the speed at which X-rays travel, approximately 299,792 kilometers per second, or about 186,282 miles per second. That's fast, and if you remember, that's the speed at which all light travels. And it never changes, all right? That's important to remember. This here is a constant, whereas the frequency and wavelength vary. So if you were asked to solve for frequency, you would use this equation here. This is the speed of light divided by the wavelength with your answer expressed in hertz. Now, if you were asked to solve for wavelength, then you would just divide the speed of light by the frequency expressed in angstroms or nanometers. And again, I know it's the third time I'm mentioning this, but it's important. The higher the frequency, the shorter the wavelength. They have an inverse relationship with each other. If you look at this chart, here you have a high frequency and a shorter wavelength. For diagnostic radiography, this is what we want because high frequency electromagnetic waves in the form of gamma rays are able to penetrate the human body and contribute to a useful or diagnostic X-ray image. Okay, so far, number one, we said that an X-ray beam was a bundle of electromagnetic photons, right? That bundle of joy that we call X-rays when high-speed electrons connect with the tungsten target of the anode inside the X-ray tube. Then number two, we talked about how these photons travel. We said they travel in sine waves, which are measured using three parameters: frequency in hertz, wavelengths in angstroms or nanometers, and velocity, which we said is always constant at the rate X-rays travel, which is the speed of light. The third thing we need to understand are the different characteristics that make up the X-ray beam. These include beam quality, beam quantity, and the difference between the primary beam and the remnant beam. Let's start with beam quality. Beam quality refers to the energy and penetrating ability of the X-ray beam. Now, we already talked about frequency and wavelength, but what affects or controls those two factors? Well, in an X-ray beam, kVp controls the frequency. Higher kVp gives the electrons more energy before they hit the tungsten target, which corresponds to higher frequency, which then equals shorter wavelengths, which means higher energy and higher penetrability for our beam. So let's say we were going to X-ray a patient's lumbar spine and we have them in a lateral position. Well, if we set our kVp factors too low, say 70 kVp, then what we're doing is lowering our frequency, lengthening our wavelength, and therefore lowering the penetrability of our beam. If we do that, what do you think will happen? Well, less X-ray photons will pass through our patient and reach the image receptor. What can we therefore say about the quality of our beam in this case? That it is a low quality X-ray beam. And so a low quality beam with lower frequency and longer wavelength is more likely to be absorbed by the patient through the photoelectric effect before reaching the image receptor. Whereas if we selected 90 kVp for this lateral view, we would end up with a higher quality beam with higher frequency and shorter wavelengths, resulting in more photons making their way through the patient to form the remnant beam, which we'll get to in a moment. Now, the second X-ray beam characteristic is quantity. Beam quantity refers to the number of X-ray photons in the beam, which is primarily controlled by MA and exposure time, or MAS when we're combining the two. Now, if you remember from X-ray production, MA controls the thermionic emission at the filament, which determines how many electrons are boiled off to form an electron cloud and therefore are available to create X-ray photons. They're waiting for that push or acceleration that comes from kVp. So in a sense, MA does not change the energy or penetrability of the photons because it does not affect waveform or frequency. So kVp controls the energy, frequency, and wavelength of the X-ray beam, whereas MAS only controls how many electrons and therefore photons are produced, not their frequency or wavelength. However, both are needed in the production of the primary beam and remnant beam that I briefly mentioned a moment ago. So let's take a look at these last two characteristics. The X-ray beam consists of two major portions, the primary beam and the remnant beam. The primary beam is the radiation emitted from the X-ray tube before it interacts with the patient. So if we look at this diagram here, the X-rays that are produced at that 12-degree tungsten target of the anode during deceleration end up spreading out isotropically, meaning they diverge equally in all directions from this point forward as they exit the beryllium window. This gives us the primary beam, the part that is released from the X-ray tube before it reaches the patient. After the primary beam makes contact with the patient, several things happen. A lot of them get absorbed, some penetrate through, and the portion that exits and reaches the image receptor is the remnant beam, also called exit, transmitted, or signal beam. This beam right here, the remnant beam, is what carries the useful information that forms a great diagnostic image that any tech would be proud of. Here's something worth remembering as well. The remnant beam is made up of less than 1% of the original primary beam because a lot of the photons are absorbed within or scattered from the patient. So if you remember, during X-ray production, only 1% is converted into X-rays that make up the primary beam, mostly Bremsstrahlung. And then less than 1% of that reaches the image receptor after it makes contact with the patient's anatomy. Hence the name remnant beam. Pretty wild, I know. Now that we understand what the X-ray beam is, how frequency and wavelength describe the energy of those photons, and how beam quality, quantity, primary beam, and remnant beam all work together, we need to look at one more important idea before wrapping up. What happens to the X-ray beam as the distance changes? Okay, this brings us to the inverse square law. The inverse square law tells us that the intensity or quantity of the X-ray beam is inversely proportional to the square of the distance. What does that mean? Well, it means that the further the X-ray beam travels from the source, the target interaction where X-rays started, to the final target, that last thing it makes contact with, which is the image receptor, the more it'll spread out and the weaker it will get by the time it reaches a certain point. So if you increase your SID, source to image distance, the beam will fan out over a large area, and what happens to the intensity of that beam? It decreases. Again, it has an inverse relationship. As the SID increases, the intensity or number of photons reaching any given area, whether it's the patient or the receptor, decreases. How does this practically apply to you as a radiologic technologist? For the technologist, the patient is the main source of scatter radiation. That means if you are standing near the patient during an exposure, you are closer to where the scatter is coming from. But if you step further away from the patient, that scatter radiation gets much weaker. How much weaker? Well, when we double our distance, the intensity is 1/4 as strong. Not bad. This is one of the best ways you can practice radiation protection. Just by doubling your distance from the patient, you can significantly reduce the amount of radiation exposure you receive. For example, if the exposure is 8 milligrays at 90 centimeters and you move to 180 centimeters, you doubled your distance. Since doubling the distance reduces the exposure to 1/4, the new exposure you would receive is 2 milligrays, which would be 1/4 of the original 8 milligrays you would have received. Speaking of math, this is the inverse square law formula. You should definitely put this formula to memory, and the best way to do that is by doing as many examples as possible. We see here that I1 is the original intensity, I2 is the new intensity, D1 is the original distance squared, and D2 is the new distance squared. Don't forget to square the distance when doing the math. A lot of students get those problems wrong because they don't square the distance. All right, let's try an example. At 40 inches, the radiation intensity is 200 milligrays. The technologist increases the distance to 80 inches. Using the inverse square law, what is the new radiation intensity? Remember, the new intensity should be 1/4 as strong. So if you did the math using this formula, it would look like this. Original intensity is 200 milligrays, original distance is 40, and the new distance is 80, that goes here. Square 80 and 40, divide those two numbers, that gives us 4, then divide 200 milligrays, our known intensity, by 4, and your answer is 50 milligrays for your new radiation intensity. Or if you want to do simple math using the 1/4 rule, you can just divide the old intensity by 4. That also would give you 50. As technologists, we use distance every day to reduce radiation exposure to ourselves, our patients, and anyone else in the room. If you can safely step further away from the X-ray source, you can greatly reduce your exposure rate. Even a small increase in distance can make a big difference because the intensity does not decrease evenly. It decreases by the square of the distance. One of the instructors in the 21-day challenge, Dr. Nicole Walton, often gives this as an easy way to understand it. X-rays spread out like light from a flashlight. The further away you stand from the source with your light, in this case the wall, the more spread out the beam becomes and the weaker it gets. Again, that is why distance is one of the easiest and most powerful ways a radiologic technologist can protect themselves from radiation, which we'll talk about when we get to radiation protection. Okay, we defined what an X-ray beam is. We looked at the significance of its frequency and wavelength, its inherent characteristics, and we just saw how it behaves under the principle of the inverse square law. Let's wrap up by looking at the fundamental properties of X-rays. First, they are invisible. We can't use our 5 senses to observe them as they're happening. Although we have a way of measuring them, we can only physically see the result they produce in the form of a radiographic image, or in some cases, the negative side effects they produce in our own bodies. Second, they travel at the speed of light in a vacuum, this X-ray tube. Third, X-rays are electrically neutral. They do not have a negative or positive charge. Fourth, they have no mass. They are weightless. Fifth, X-rays cause ionization, which is the process of gaining and removing an electron from an atom within the patient's body. An atom is normally neutral because it has the same number of protons and electrons. But if enough energy knocks an electron out of its shell, the atom becomes a positive ion. That's ionization. Sixth, X-rays cannot be focused by a lens. What does that mean? We cannot bend X-rays into a sharp point like visible light. With a photo or video camera, we can do that and therefore focus where we want it to go because it has a lens. An X-ray machine is different. So we have to control the beam by limiting its size, distance, and direction instead. And we do that with collimation, which narrows the X-ray beam, SID, which controls distance from source to image receptor, focal spot size, which affects recorded detail, positioning, which controls how the anatomy is projected on our image, and grids, used to absorb scatter before it reaches the image receptor. Okay, seventh, X-rays are polyenergetic or heterogeneous in nature, which means they come in all levels of energy, wavelengths, and penetrating power. Eighth, they can penetrate the human body due to their high frequency and short wavelengths. Ninth, they can produce secondary and scatter radiation. 10th, they can cause biological change to the parts of the human body they interact with. 11th, they can cause certain substances to fluoresce or glow. And lastly, number 12, they follow the inverse square law, which helps us reduce the amount of radiation exposure to ourselves. All right, that covers everything you need to know about the X-ray beam. Frequency and wavelength, beam characteristics, inverse square law, and its fundamental properties. Master these concepts and you'll gain greater control over the invisible force that determines image quality, patient dose, and even your own protection as a radiologic technologist. Now, in the last lesson on the principles of radiation physics, I'll be covering photon interactions with matter, where we take a look at the photoelectric effect, Compton and coherent or classical scatter, and the attenuation of various tissues. So make sure to check that one out. If you want to master the concepts you learned here today, take the free exam provided for you in the link below. Teach what you learned here to someone else. And if you need help passing the ARRT registry exam, check out the 21-day registry review challenge at radtechregistry.com. Lastly, don't forget to share this lesson with someone you like, hit the subscribe and notification button, and speaking of like, don't forget to do the same for this video. As always, thanks for watching, and I'll see you in the next one.